diabetic retinography, get prediction from retinal fundus. So here are some heat maps. If you notice, there's some small spots. So they are mainly responsible for diabetic retinography grading. So the same way, if you go to the particular text classification task, so you will notice there are some red colors or some colors. Those colors are actually mainly colored words are mainly responsible to get the activation of the model, or you could say that those are the are responsible to get the prediction. Now, how could we build this one? If you notice here that this is the corresponding in logistic regression, there is a straight line, and there is a, if we say there is a TR production rate, it's a reduced non-normal, then astigmatism, ES, then age, non-symbiotic and symbiotic. So in this way, we could, if you notice this particular decision tree, you could make a decision like here. If and else, this kind of condition is there, and rules can be combined using that AND operation. Or explain this is actually, you could explain the things properly, but here whenever you are getting some neural network, so there is a no you can say the corresponding model is black box model, right? So whenever it is a black box model, so on that case it would be very difficult to explain the model. So people could do what they will try to get some inputs and use some interpretable model like a decision tree to mimic or train the decision tree based on those classified sample by the model and try to explain based on those similarity. So we'll describe this kind of models in my discussion. So interpretability, accuracy, if you notice, accuracy of the neural network is very high, whereas interpretability is very low. Whereas random forest is interpretability is better than neural network, but its performance is little bit lower. Whereas decision trees accuracy is little bit lower than random forest and neural networks, but its accuracy is also lower, and linear regression is much more lower than the decision tree, because linear decision tree can deal with the non-linear region also, whereas linear regression normally deal with the linear early separated data. So in certain setting, accuracy interpretability tests may exist. So here, if you notice, can build interpretable accurate model. So on that case, you could need to make more focus on local regions. So there is two types of approaches. This is global approaches or local approaches. So in a global approaches, so all the samples will be passed through and try to get some kind of explanation based on the sample. The sample might be the validation set. If your training set is available, this would be your training set, but model is not known to you. Whereas in the local cases, only single samples will be considered for the procedure, or we need to make decision based on that one. So complex model might achieve higher accuracy. So inherently interpreted model versus post-hoc explanation. So sometimes you do not have enough data to build your model from scratch. This is very important, because as I mentioned that training data might be required for might be used to get post-hoc analysis, but sometimes it might not be available. On that case, we could use some kind of simulation data, etc. or you could use some kind of validation data to validate your model. So you have to understand the property of the black box to deal with that. So if you can build an interpretable model which is also adequately accurate for your setting, do it. Otherwise, post explanation come to the rescue. Now we'll discuss first the decision tree. Before going to the decision, actually, first we will discuss about the logistic regression model, then decision tree and rule based model. So first here. Commonly used interpretive model, that is the linear regression, logistic regression, and the decision tree. So an overview of interpretable model types and their properties. A mod, so a model is linear if the association between features and the target is model linear, right? And a model with a monotonicity constant ensures that the relationship between a feature and the target outcome always goes in the same direction over the entire range of the features. So monotonicity is useful for the interpretation of a model because it makes it easier to understand a relationship. So interaction can improve predictive performance, but too many or too complex interaction can hurt interpretability. This is very important actually. Too complex interaction is also not be desired. So if you just notice about the three things, linear regression, logistic regression, decision tree. So linear regression is linear obviously, and it's a monotone. Yes, no interaction, task regression. Logistic regression is not a linear. You know there is some exponential probability will be introduced with the linear regression model to get the logistic regression, and monotone yes, and interaction no interaction is there, and task is classification task, right? Whereas this decision tree, this is not a linear, as I mentioned. That decision tree could be used for non-linear output classes also. So it is monotone to some extent, but not always. And interaction, there might be some interaction is there, and decision tree could be utilized for both regression task or classification task. So a linear regression model predicts the target as a weighted sum of the feature inputs. What is some of the feature input? The linearity of the learned relationship makes interpretation easy. The linear regression model mainly. Is the slide visible? Hello. Oh, till now, no. Oh my goodness. So please, so I have discussed without a. Sure, just for a moment. Till now, I have discussed the very basics. Just visible now, no? So we have reason why interpretation we have discussed about this chair example. So that's to understand the philosophy of interpretation here. So if you have any question, because you may ask. So here, this DARPA challenge face recognition task and different uses. We are in the golden age, and this is the main problem what I have discussed. That's the Tesla hit path police car while using autopilot. Who will take the responsibility? There are some biasness in the algorithms, some original misperturbation, some adversarial example here, some legal issues which we have discussed. So interactive feedback here. So current state of the machine learning as we discussed. So main problem what I have discussed here. We do not trust the model because it might be wrong any moment. We do not know what happens in extreme cases. Mistakes can be expensive or harmful. Does the model make similar mistakes as human? This is very important point. How to change the model when things go wrong. Interpretability is one way we try to deal with these problems. So we have already discussed that there is no standard definition about the interpretability, and these are the way like equation of a particular logistic regression or decision tree. We could explain an image to its targeted class, especially for the diabetic retinography based on their grade. So these are the some heat maps, or we could identify particular text based on some words within the text, and we can build inherently interpretable predictive model using the logistic regression or the corresponding decision tree or pre-built model. Here this is a model, but we do not know what is there. So what we could do, we could we could use some kind of samples here, and these samples will be fed to the model, and then it will give some output, and this output will be treated as a training example for the particular decision tree, so that we could explain that one, because decision tree is inherently interpretable. So if you go for the accuracy and interpretability, if your accuracy, neural network accuracy high, random forest those are low, but their interpretability is high. So and even we could use some local interpretability model to explain more complex model, and post-hoc explanation might also be required in some cases when we do not have any prior knowledge about the model. So interpretive model which is also adequately accurate for setting, we need to develop the corresponding model, and post-hoc explanation come to the rescue on that case. Now here we'll discuss about the interpretable model. So this model, first we will discuss about the linear regression, then logistic regression, then we will discuss about the decision tree. Later we will discuss about the model agnostic approaches, both global and local. Just for a minute. Any question till now? Any confusion here? Okay, then so interpretive model regression classification, we have already discussed about the linearity, monotonicity, as well as interaction, because too many or too complex interaction can hurt the interpretability, but it improves the performance, right? So if you notice here, linear regression here, if you notice, uh, linear regression is linear, monotone, and interaction no, and task is regression. Logistic regression, linear no, monotone yes, interaction no, and task is classification. And decision tree, it could be utilized for both classification and regression purpose. And it is not linear, because we know that decision tree could be utilized to separate non-linear, only separable data also. And interaction is there. So linear regression model predicts the target as a weighted sum of the feature input. The linearity of the learned relationship makes the interpretation easy. Linear regression model have long been used by the statistician, computer scientist, and other people who tackle quantitative problems. Regression target y on some features x can be represented as y is equal to beta 0 plus beta 1 x1 plus you know that beta p xp plus some error is there. Here from the equation you could easily identify the weight of the particular features. For example, x1, x2 to xp, if these are the features, and beta 1 is their corresponding weights. So in other words, we could say beta j represent the learned feature weights or coefficient, and first weight in the sum beta 0 is called the intercept, and epsilon is the error, that is the difference between the prediction and the actual outcome. The important point, errors are assumed to follow a Gaussian distribution, which means that we make error in both negative and positive direction, and make many small errors and few large errors. And here how to train, I think all of you know that one, right? So here first beta 0 beta 1 all will be initialized randomly one, and then after that we will get some kind of error, and then you could make some kind of gradient descent, and you could adjust the weight, that means that beta 0 beta 1 etc., so that it could be updated accordingly. So for this, actually, what would be the objective here? So optimum one. So beta cap is R minimum, because our objective will when in the predicted class, target class and the predicted class, their differences become low. So objective would be to optimization function, that is R min, beta 0 to beta p. So this square method is usually used to find the weights that minimize the square difference between the actual and estimated outcome, as you notice here. So any confusion here? Is there any confusion? Okay, then you could. So linear regression and easy to understand interpretation on a modular level, that is the weight, right? As we understand that this beta 0 beta j, that could be updated with every iteration. Example, in the medical field, it is not only important to predict the clinical outcome of a patient, but also to quantify the influence of the drug. At the same time, it takes sex, age, and other features into account to make it an interpretable model, or explain it in an interpretable way. And here, actually, whatever may be the output, we will try to do that one or interpretable. Normally not, we will try to make at least some kind of confidence interval. So estimated weights come with confidence interval. A confidence interval is the range of the weight estimated that cover the true weight with a certain confidence. So for example, here 95% confidence interval means for this cases actually a true weight in 95 out of 100 cases. And for example, a 95% confidence interval for a weight of 2 would be range from 1 to 3. The interpretation of this interval would be, if we repeated the estimation 100 times with newly sampled data, the confidence interval would include the true weight in 95 out of 100 cases, given that linear regression model is the correct model for the data. Now, the model is correct model depends on whether the relationship in the data meets certain assumptions, which are linearity, normality, homoscedasticity, independence, fixed feature, and absence of multicollinearity. So what does it mean? Linearity, as we mentioned, the linear regression model forces the prediction to be a linear combination of features, which is both its greatest strength and its greatest limitation. Linearity leads to interpretable models, and effects are easy to quantify and describe. They are additive, so it is easy to separate the effects. Whereas normality, it assumes that the target outcome given the feature follow a normal distribution. If the assumption is violated, so the estimated confidence interval of the feature weight are invalid. This is because in the confidence interval for any Gaussian model, this is just 1.96 of its corresponding standard deviation in both the plus and minus side. So homoscedasticity, the variance of the error terms is assumed to be constant over the entire feature space. Example, you want to predict the value of a house given the living area in square meters. You estimate a linear model that assumes that regardless of the size of the house, the error around the predicted response has the same variance. So this is very important concept, but it makes some kind of confusion also. Suppose the average error difference between a predicted and actual price in your linear regression model is 50,000 euro. If you assume homoscedasticity, you assume that the average error for 50,000 is the same house for the cost 1 million as well as cost 50,000 euros, or cost only 40,000. On that case, it will be negative. So this is unreasonable, because it would mean that we can expect negative house prices. That is not possible in reality. So these are some important things you need to be remembered. And independence, it is assumed that each instance is independent of any other instances. If you perform repeated measurements such as multiple blood tests per patient, the data points are not independent. Now, fixed features. Fixed means that they are targeted as given constant and not as statistical variable. This implies that they are free of measurement error. This is a rather unrealistic assumption. And another important point, absence of multicollinearity. So collinearity is very important whenever two features are there, and if they are collinear in nature, so it will be very difficult to identify the contribution of them properly whenever they will act simultaneously. So in general, in the particular regression model, we do not want highly correlated features. So strongly correlated features are not desirable, because this messes up the estimation of the weights. In a situation where two features are strongly correlated, it becomes problematic to estimate the weights, because the feature effects are additive, and it becomes indeterminable to which of the correlated features to attribute the effects, as I discussed earlier. Now, interpretation. The interpretation of a weight in the linear regression model depends on the type of the corresponding features. So there are several types of features: numerical features, binary features, categorical features are there. Categorical features, these are some values in alphabetic form, like a feature with a fixed number of possible values. An example in the feature float type, possible categories of carpet, laminate, etc. Whereas intercept beta 0, the intercept is the feature weight of the constant feature, which is always 1 for all instances. Most software packages automatically add this one features to estimate that one, like a like a W0 X0 or beta 0 X0 X0 is the features that is a bias, because it is treated as 1 in the most of the software. Now, interpretation. This is very important thing. So what we are going to discuss now. The interpretation of the feature in the linear regression model can be automated by using following text templates. So interpretation of a numerical features and increase of features x k by 1 unit increase the prediction y by beta k units when all other features values remain fixed. This is very important. Like we are dealing with single features, keeping all the features constant, and we are increasing 1 unit the features value. On that case, the prediction output will be prediction of the beta k units. So, uh, that means the weight of the this particular features will increase by beta k unit to make the prediction. So now interpretation of categorical features. So changing features xk from the reference category to the other category increase the prediction for y by beta k when all other features remains fixed. So another important measurement for interpreting linear models is the R squared measurement. The formula for calculating R squared is here 1 minus SSE. Uh, uh, Here SSE is given sum of squared here. Here you could get that's the yi minus this is a predicted yi the differences, and here this is a SST is defined the corresponding variance with the predicted plus and error sum, and here yi minus y mean square. Now, importance of the features. Actually, this is very important for the interpretable model. Like it is defined by T statistics for the regression model. That is the T beta cap j is equal to beta cap j divided by standard error beta j. So, if you have a features as a particular column, and there is the, if you want to define a particular beta j, and then you have the what kind of error it will get. You have to calculate that one, and you have to calculate the contribution of the feature like that. So how could we represent these things? So visual interpretation. This is very important things here. In-person weight table, weight matrix can be visual in weight form. So this is actually bike rental problem. Bike rental problem is rental of a bike. It depends on different features. So this is a working, whether it is a working day or not working day. Is there any wind speed is there? Whether is rain or snow or storm, and whether is misty or temperature is what is the temperature, what is the summer or season, what is the spring season, and whether it is a fall season, and there is a holiday or day since 2011, it will be calculated. That was how many number of bikes would be rented. So from these things, if we could, and there is some statistics there, and from that statistic, it was found that this particular weights are spread over any over this particular minus 2000 here. There is some negative values are there, and there is some positives value, and there some samples they are affected positively, some samples are affected negatively, some effects are very low. For example, wind speed effects negatively, but very low, whereas rain, snowstorm, the effects very high. I mean, holiday effects the high. So these are the way we could explain it, some weight plot. I mean, some kind of effect plot. Weight plot we could use only the weight of that particular features, but some in effect plot we use not only the features, we use the corresponding features multiplied by the corresponding weight. Like in the beta 1 multiplied by x1, and then we will plot that one, and then we will get if we plot, then we will get the box plot here. Effect plot can help you to understand how much the combination of weights and feature contributes to the prediction in your data. The effects can be visualized with box plots. Now, But the problem is that this kind of interpretation is quite easy for small number of samples. But if your number of samples are very high, number of features are very small, then you could represent them easily through this kind of plot. But if your number of features are very high and number of feature samples are low, on that case it would be difficult to interpret them. Then on that case you have to do what you are, this is called actually sparse linear models. You need to reduce the number of features. There are different ways you could reduce. The one of the important concept, that is a lasso. Lasso is an automatic convenient way to introduce sparsity into the linear regression model. Lasso stands for least absolute syncage and selection operator, and when applied in a linear regression model, performs feature selection and regularization of the selected feature weights. For example, here minimization of beta 1 by n and summation of yi minus xi transpose beta square. So this is the corresponding main model. Our objective is to minimize that one. So now here we are using a terminology. This is a lambda beta 1. This is actually lasso terminology is used as a penalty function. So the term beta 1, the L1 now the feature vector is to parse a penalization of large weights. So here if your lambda is there, large weights to be penalized. So with increasing penalty of weights, fewer and fewer features receive non-zero weight estimates. So if you notice, this is in the logarithmic scale right here. So you could understand it is around 10 to the power 5 the value of alpha here. This lambda it's 10 to the power in logarithmic is 10 to the power 5. And here if you increase the size of the corresponding samples, then you notice this here. If you increase here, if you notice this become, see the number of features when it is lambda is low, 12, 12, 12, then it is decreasing. If you are using the value of lambda, increasing the value of lambda here, and here it is decreasing at 2. So with increasing penalty of the weights, fewer and fewer features receive a non-zero weight estimates. These curves are also called regularization paths. The number above the plot is the number of non-zero weights here. So other method of sparsity removal techniques are there. There is a P-passing model. I think these are well discussed in the field of feature selection technique in the domain of machine learning or pattern recognition. So in P-passing method, manually selected features, you can always use expert knowledge to select or discard some features. The big drawback is that it cannot be automated and you need to have access to someone who understands the data. This is very important point. Second one, univariate selection. An example is the correlation coefficient. You only consider features that exceeds a certain threshold or correlation between the features and the target. The disadvantage is that it only considers the features individually. Some features might not show a correlation until the linear model has accounted to some other features. Those ones you will miss with the univariate selection methods. And stepwise selection, this is forward selection. In forward selection, you may start from one particular features. Now you may include another features and try to evaluate the performance which is better than your previous one. Then you could say it has some kind of contribution, right? Then you could consider, otherwise you could discuss that one. So in other words, you could say fit the linear model with one feature. Do this with each feature. Select the model that was best for highest R squared. Now again the remaining features fit a defined version of your model and adding these features to your current best model. This is very important too. In forward selection, there is another approach. They say you could first sort them according to their performance, then I try to add them, and if the performance improved, then you could include them or not. So another is backward selection. It is just opposite. Here you need to remove the features. So study the model accounts all features and try out which feature you have to remove to get the highest performance increase. So you could remove one after another, and you could get the which one is the better. Consider that one, and the next time you will remove the another features for that particular selection. This should be recursive procedure. Now, advantages. The tree structure is deal for capturing interaction between features in the data. The data ends up in distinct groups that are often easier to understand, that points on a multi-dimensional hyperplane. As in linear regression, the interpretation is arguably pretty simple because we know tree structure also has a natural visualization with the nodes and edges. There is no need to transform features. In linear models, it is sometimes necessary to take the logarithm of feature. A decision tree works equally well with any monotonic transformation of a feature. Disadvantages: tree fails to deal with linear relationship. Any linear relationship between an input features and the output outcome has to be approximately by creating a step function. This is not sufficient. This goes hand in hand with the lack of smoothness. Trees are also quite unstable because a few changes in the training data set can create a completely different tree. But decision trees are very interpretable as long as they are short. The number of terminal nodes increases quickly with the corresponding complexity will be higher and interpretability will be lower on that case. So any question here? Is there any confusion till now? Confident, then we could go ahead. Now, decision tree, linear regression, logistic regression model fails in situation where relationship between features and outcome is here actually in the logistic regression you have to just plot them in the logistic way, and you could use them for classification purpose actually, because here we have discussed mainly for the regression purpose, but if you use the logistic regression, then you could utilize them for defining the corresponding classification task. And whereas in decision tree would be utilized both regression as well as the classification task. Tree-based models split the data multiple times according to the certain cutoff values in the features, and those splitting different subset of the dataset are created, and with each instance belonging to one subset. The final subset are called terminal or leaf nodes, and the intermediate subsets are called internal nodes or split nodes. To predict the outcome in each leaf node, the average outcome of the training data in this node is used. This can be used for classification as well as a regression. Decision tree here following formula, because as we know, we need to describe the interpretability of a decision tree, and you could remember a decision tree could be select a particular features based on either Gini index or some entropy. So Gini index, the Gini index tells how impure a node is, and if all classes have the same frequency, the node is impure. If only one class is present, it is maximally pure. So variance and Gini index are minimized when the data points in the nodes have similar values for y. So whenever we are talking about the Gini index, if it is low, then we will select that particular lowest features having Gini index, for which we could split the corresponding attributes, and on the other hand, information gain, high information gain are normally considered. So best cutoff point makes two resulting subset as different as possible with respect to the target outcome. And here decision tree entropy is there, and information gain are also some. So decision tree, there's a importance, features importance. Starting from the root node, you go to the next node, and S tells you which subset you are looking at. Once you reach the leaf node, node tells you the predicted outcome. All the edges will be connected to by AND, right? So overall importance of the features in a decision tree can be computed in the following way. First, split the corresponding node for which the feature was used and measure how much it has reduced the variance or Gini index compared to the parent node. So you may compare the child node as well as the parent node, the Gini index, and there is a what is the reduction of that. The sum of all importances is still to 100. This means that each importance can be interpreted as share of the overall model importance. So this is the corresponding relationship. Here each instance falls into exactly one leaf node subset Rn. IRM is the identity function that returns 1 if x is in the subset Rm or 0 otherwise. If an instance falls into a leaf node Rn, the predicted outcome y. I dash is equal to corresponding CL, and where CL is the average of all training instances in the leaf node Rn. So this feature importance could be described with this formula also. This tree decomposition. Individual prediction of a decision tree can be explained by decomposing the decision path into the one component per feature. We can track a decision through the tree and explain a prediction by the contributions added at each decision node. The root node in a decision tree is our starting point. If we are to use the root node to make prediction, it would predict the mean, the outcome of the training data. Obviously, this could be decided by either by the Gini index or by the information gain. So, if low Gini index, lowest Gini index particular attributes will be selected for the first division. With the next split, we either subtract or add a term to this sum, and depending on the next node to the path, to get the final prediction, we have to follow the path of the data instance that we want to explain and keep adding to the formula. So here the attributes f dash x and y is the mean of the instances. For classification, it will be the probability. For regression, the average values of that one, and this plus the split contribution of dx. So this could be represent the features contribute of jx. This could be defined by the previous concept here by Gini index difference between the parent node and the corresponding child node. The prediction of an individual instance is the mean of the target outcome plus the sum of contribution of the d-split that occur between the root node and the terminal node where the instance end up. So we are not interested in split contribution though, but in the feature contribution, a feature might be used for more than one split or not at all. We can add the contribution for each of the p-features and get an interpretation of how much each feature has contributed to the prediction. This is very important. As if you notice here, this is the bicameral problem here. So this is case is 2011. It's less than this one, and this is greater than that one. And then again we are using the same particular features. This less than 100 5.5. You will get n is 106 number times of occurrence or bike rental. and greater than 305 and but less than less than 434.5. On that case, it is in 329. But if you it's greater than 434 and the temperature is less than 11.662, on that case, only 70 samples are used for appropriate classification, and here for N2 to 26, and there these are the means of those samples are represented here. So regression tree fitted on the biquintal data. The maximum allowed depth for the tree was set to 2. The 10 feature days since 2011, and the temperature sorry, have been selected for the splits. Sorry, the box plots show the distribution. The advantage of this one. Sorry, just 1 minute. The tree structure is ideal for capturing interaction between features in the data. The data ends up in distinct groups that are often easier to understand than points on a multidimensional hyperplane as in linear regression. The interpretation is arguably pretty simple. The tree structure also has a natural visualization with its node. If it is just a 2 level, then it could easily be. But whenever a tree there is a number of depth is increasing, then it will be very difficult to get that one. And tree fails to deal with linear relationship, right? Any relationship between the input feature and the outcome has to be approximated by splits. Creating a step function, this is some cases not efficient. This goes hand in hand with the lack of smoothness. So slight changes in the input features can have a big impact on the predicted outcome, which is usually not desirable. And trees are also quite unstable. A few changes in the training data set can create a completely different tree. So these are the some challenges. Now these are the approaches. What we have discussed is the model-specific approaches, right? So here, if you try to discuss, then you have to discuss with the logistic regression, linear regression, or the corresponding decision tree. But there are some other approaches out there. Model agnostic approach. This is a this could be applied to any model actually. It could be applied for the deep learning model. It could be applied for super vector machines. So model agnostic interpretability model are techniques that can be applied to any machine learning model regardless of its underlying architecture or complexity. This is very important point. And as we discussed at the beginning that whenever the corresponding accuracy is increasing, then with this the corresponding interpretability of the model become low. So therefore it would be difficult to explain them properly. But in medical domain, actually, without interpretability, the system could not be relied. So therefore, if in the literature, if you go through some models are there which performs very high accuracy in a particular domain, but those models are not being acceptable by the medical community due to because they are not explainable by the human, or it is not understandable to the doctors properly. So now what is the task of the researchers to make the some kind of interpretation of the outcome so that doctors or the human could understand that. So here they obtain explanation by but in model specific approaches you could not do that one because whenever you are getting a system you do not know which system is used and how many parameters are there and etc. and manufacturers or developer could not share the details of that. So on that case, how would you define the explainability? So here, they often explanation by perturbing or mutating the input data and obtaining sensitivity of the performance of this mutation with respect to the original data performance. Any question here? Any question? So model agnostic methods, there are two types of methods, and global model agnostic method and local model agnostic methods. In global model agnostic methods, there is this will be explained with respect to the all the samples simultaneously, whereas local model agnostic methods, here only single predicted class will be considered for describing the corresponding interpretability of the model. So in global model agnostic model, there are several methods are there. We will try to discuss some methods. Here, partial dependence plot. First, an accumulated local partial dependence plot. So if you notice here, global model structure will use a partial dependence plot, accumulated local effect plot, feature interaction, permutation, feature importance, global surrogate, whereas local model agnostic method will discuss individual conditional expectation, local interpretable model agnostic explanation line, Shapley values, Shapley additive explanation. So now we could start with the partial dependence plot. So partial dependence plots PDP shows the dependence between the target response and a set of input features of interest, marginalizing over the value of all other input features, the complement features, we could say. Intuitively, we can interpret the partial dependency as expected target response as the features of the input feature of interest. So let's suppose you have a model with 4 features, right? So you could just measure one with respect to others with that means a particular features will be varied with respect to other features remain fixed. So explain target response as a function of input features, and due to the limits of human perception, the size of the set of input features of interest must be small. Usually 1 or 2, thus input features of interest are usually chosen among the most important features. So you could select this most important feature using some ranking technique of the features. So partial dependency, this is a cap xs, and this is the expectation of xc, xs and xc. So xs is what? X is the set of features that we want to plot PDP. So these are the normally 1 or 2 in general, because higher degree features could not be plotted into dimension, 3-dimensional, it requires more. So and xc is the rest of the features. X is the features you want to explain properly, and as this is the best features, so you could say this is the primarily responsible for making the decision. And this could be represented in practice. This Sxs is 1 by n. So this is a summation, this expectation. Instead of integration, we use this formula to get the corresponding partial dependency plot. And let's take an example of partial dependency plot. Not here. So cervical cancer data set here. This is from the UCI repository. Features, this will actually determine the risk of the cervical cancers. Age in years, number of sexual partners, for sexual intercourse, age in years, number of pregnancies, smoking, yes or no, smoking in years, hormonal contraceptives, yes or no, hormonal contraceptive in years. Interpreting their devices, yes or no, number of years with an interpreting device, IUD. Has patient ever had a sexual transmitted disease, yes or no, number of sexual transmitted disease diagnosis, time since first uh, diagnosis, times is last study diagnosis, the biopsy results are healthy or cancer or target outcomes. These are the some features. Based on this, you need to predict the risk of cervical cancer later. So, and if we take the features like a number of ages, and we remain these all the features are fixed, and we divide these ages with a particular interval, right? So, and if we plot them, then predicted cancer probability. This is some dependence on the other features. That is, it is actually not the only age features. It is actually combining with other features. That is a jointly occurred features, and then you could predict. This is it is a 0.1. It's a very high. Even it's a in this lower ages, this is very low, but in higher ages, after uh, 40, you may notice this is increasing. Whereas, and here this model performance is based on the random forest, and this is for PD for one features. So now cancer probability based on age and years with hormonal contraceptives. That is how many years their contraceptives pills are taking. So from there, if you notice after 10, it is the probability is increasing, and then it will become more or less same. Now here, if we want to make the partial principal with two features, how could we do that actually? So if you notice here in this particular figure, so you may notice there is age and there is a number of pregnancies here, and try to here age is fixed and number of pregnancy varies, and at the same times if you fix the number of pregnancy or ages varies, rest of the features are remain fixed, then you will get this kind of plotted. And if you notice these regions, this is a there's a 0.125 these values are not there. So age and number of pregnancy both are certain things, you will get some values. So these in this way actually these features are correlated. This is actually partial dependence plot. This is very important because most of the model agnostic methods making some kind of assumption about the partial dependency plot. So cancer probability based on the interaction of age and number of pregnancies here. Now partial dependency plot advantages. The computation of partial dependency plot first is intuitive. The interpretation is clear for uncorrelated data. This is very important. Uncorrelated data making some assumption that the corresponding features are uncorrelated. Otherwise, it will not perform well. So we'll discuss in the next slide about that one. So partial dependency plot are easy to implement. Calculation for the partial dependency plots has a causal interpretation because you could if they are joint contribution, etc. The realistic maximum number of features in a partial dependence function is true due to limitation of visibility. Some partial dependence plots do not share the feature distribution. The assumption of independence will not work always. Heterogeneous effects might be hidden because partial dependence plots only show the average marginal effects. Any confusion here? Any question?
No, sir.
Now, accumulated local effect plot. Disadvantage of partial dependency plot, as I mentioned, there is a when there is a correlation is there, they will not be trusted at all. Completion of the partial feature that is strongly correlated with other feature involves varying prediction of artificial data. instances that are unlikely in reality. So this can greatly be biased the estimated feature effect. So how could we remove this one? So if you notice, this is a correlated that data. So if both are increasing, you will get some increased one. So here, partial dependency plot. If you plot them, you will get most of the areas will remain vacant because they are highly correlated. So strongly correlated features x1 and x2. So to calculate the feature effect of x1 at 0.75, if you could notice the effects, you could get this kind of curves. And the PDP replaces all instances with 0.75. But here, if you notice this one, these are the some which is here. These are the some effects are there. So first we have the distribution of x2 at x1 is the same as the marginal distribution of x2. So these are not the same, right? So combination of x1, x2, and x1, which is the PDP use of calculation the average effect. So we could not get the average effect. Solution for calculating feature effect using this condition distribution is called marginal plots or M plots. So M plots uses the conditional distribution to calculate the feature effects. So M plots avoid averaging prediction of unlikely retention, but they mix the effects of features with the effects of all correlated features. Here, if you notice that one, so we will instead of that one, instead of the entire regions like in previous cases, the entire regions of all the data, here we are considering only the local regions where our features are there. So local regions, they are using some kind of effects of these regions. So strongly correlated feature x1 and x2 M plots average over the conditional distribution. Here the conditional distribution x2 and x1 is equal to 0.75. Averaging the local prediction leads to mixing the effects of both features. So ALE plots solve this problem also based on the conditional distribution of the features different in prediction. So here we are considering with respect to x variation. Now if we to vary x2 with respect to how could we do that? So here if we could just first divide that one. So we are considering the local effect. So here we could divide these regions local. If first local effects we consider, we could divide this part. So here accumulated local effects ALE plots is considered FJK. So here NJK is a number of interval, that how many interval we have considered. For example, here Z01, Z1, Z2 to Z51 different interval. So N1, N2, N3, N4, N5. So from here, this is corresponding that one, and if JK ZK J X minus J and the corresponding if ZK minus 1 value of ALE can be interpreted as the main effect of the feature at a certain value compared to the average prediction. So here we are making some kind of prediction, average prediction of the data. ALE estimate minus 2 and xj is equal to 3 means that when Z feature has value 3, then prediction is lower by 2 compared to the average prediction. So here, so we could get that plot. So calculation of ALE for features x1, which is correlated with x2. First, we divide the feature into intervals, vertical lines for the data instance point in an interval. We calculate the difference in the prediction. When we replace the feature with the upper and lower limit of the interval, these differences are later accumulated and centered, resulting in the ALE curve. And here, 2D cases, we place a grid over the two features. In each grid cell, we calculate the second order differences for all instances within. We first replace the value of x1 and x2 with the values from the cell corners. If A, B, C, D. If you notice here, represent the corner prediction of a planetary distance as labeled in the graphics. Then the secondary difference is D minus C and B minus A. This means secondary difference in each cell is accumulated over the grid and centered. So, but there are some how it will be visualized here. So, because if we just think about the edge. So, if you notice here, this is a very zigzag, then it is very high, and this is the zigzag high. This is ALE for one features. ALE of biopsy based on age and years with hormonal contraceptives. So, ALE for two features, then we could use the concept here, those local regions, and here F is the corresponding random forest, and if we plot this, we will get this kind of correlations. Now, advantages: ALE plots are unbiased, which means that they still work when features are correlated. ALE plots are faster to compute than PDPs and scale with big O of n, since the largest possible number of intervals is the number of instances with one interval per instance. The entire prediction function can be decomposed into sum of lower dimensional ALE function. So, interpretation of ALE plots is clear. Conditional on a given value, the relative prediction changing the feature on the prediction can be read from the ALE plot. But there is a disadvantage, that is a effect across the interval, because if you notice the zigzag curve, right? So this will be calculated locally, but across the interval is not permissible. The features are strongly correlated. ALE effects may differ from the coefficient specified in the linear regression model when features interact and are correlated. And there is become a bit shaky, many small ups and downs with a high number of intervals. Unlike partial dependency plot, ALE plots are not accompanied by IC curve with individual component. And so we will discuss those things later. The implementation of ALE plots is much more complex. Now, feature interaction, another model agnostic methods globally. When features are interact with each other in a prediction model, the prediction cannot be expressed as a sum of feature effects, because effects of one feature depends on the value of the other features. Those who are working on in the field of machine learning, they know that just ranking the features and combining the features does not provide always the good results, because if they are highly correlated, their performance could not be improved. Even if their features are mutually inversely correlated, then performance instead of higher it will be lower. So when features interact with each other in the prediction model, the prediction cannot be expressed as a sum of feature effects, because effect of one feature depends on the value of other features. In machine learning model makes a prediction based on two features. We can decompose the prediction into four terms: a constant terms, a term for the first feature, a term for the second features, and a term for the interaction between the two features. The interaction between, this is very important. There is a constant will be there, then there is the first, second, and interaction term. Interaction between two features is the change in the prediction that occurs by varying the features after considering the individual feature effects. So if you notice here, feature interaction, this is a house price prediction, and here if you say location, size, and it's just the prediction, and here's the bad small. This is a location bad, size small, 1,50,000. Location bad but the size is big, then 2,50,000. Location good, size small, is a 2 lakhs, and good big, it's a 3 lakhs. And from there, if you notice, bad small, this is constant because this is the lowest one. It's 150, and now if we change, let's say small to big change is 1 lakhs, and bad to good change, it's a 50,000. Now if you both are changed, that is a bad to good here and small to big, so this would be added with this constant term, and if you notice this is a 3 lakhs. So these two can fully explain the model prediction. There is no interaction effect because the model prediction is a sum of single feature or effects for size and location. But for these cases, so here you will not get the linear relationship like that. So here the another interaction is there. This is 1 lakh if both are there, because here previously it was 3 lakhs, but here it is a 4 lakhs. So 1 lakh additional based on their interaction. This is good and big. This is an interaction between size and location, because in this case difference in prediction between big and small house depends on the location. So feature interaction, this is based on the partial dependency between the two features xj and xk, and this is this pj jk, and if they are independent, then pj jk becomes equal to this. If this interaction is negatively correlated, then it will become 1. So the same applies measuring whether a feature j interact with any other features. So previously it was between the two features we are calculating the interaction, but now here we are calculating the interaction between the features j and other features. So feature interaction Feynman statistics. So if you there is a random forest, it has been noticed that the overall interaction strength, this is the individual interaction strength, hormonal contraceptive years, number of pregnancies, sexually transmitted disease, or number of diagnoses, age for sexual intercourse, IUD years, smoke years, number of sexual partners. These are varied, right? Now they are for individuals. So interaction strength for each feature with all other features for a random forest, predicting the probability of cervical cancer, the years of on hormonal contraceptives as the highest relative interaction effect with all other features followed by the number of pregnancies. Now feature interaction for many statistics. So here two-way interaction. The previous cases it was single interaction. A two-way interaction, it could be calculated based on this formula, and this is an age now age and number of pregnancy, hormonal contraceptive years, number of pregnancy. Now it's become more active, age and number of pregnancies, whereas here hormonal contraceptive and number of pregnancy, this will become lower. So you could notice that overall interaction strength varies whenever they are interacting with each other. So the two-way interaction strength is statistic between number of pregnancy and each other feature. That's dominantly. There is a strong. So here number of pregnancy remain fixed and all others are varied. And we notice from age, and this is the highest one. So finite statistics, the major advantage, statistics has a meaningful interpretation. Interaction is defined as the share of variance that is explained by the interaction, and this statistics is dimensionless. It is compared across features and even across model. Statistics deals all kind of interaction regardless of their particular form. It is also possible to analyze arbitrarily higher interactions, such as the interaction strength between 3 or more features, because we have no we could utilize the corresponding formula of statistics. Now, disadvantage: the interaction statistics takes a long time to compute because it is computationally expensive. Interaction statistics works under the assumption that we could subtle features independently. If the features correlate strongly, the assumption is violated. We integrate over features combination that are very unlikely in reality. Sometimes results for small simulation do not yield the expected result. This is very important. You need more analysis. permutation of the features important. And so this model is very simple. You have a defined features. So these features remain permuted a particular features value. This will be permuted with defined features. So that means one features value will be permuted over all other features, and you will get defined results, and then you could understand how it would affect the corresponding things. So you could say permuted feature importance measure the increase in the prediction error of the model after we permuted the features value, which breaks the relationship between the feature and the true outcome. Because after permutation, we will check the outputs through the model. We measure the importance of the features by calculating the increase in the model's prediction error after permuting the feature. A feature is important if supplying its values increases the model error, because in this case the model relied on the feature for prediction. The feature is unimportant if supplying its value leaves the model error unchanged, because in this case the model ignores the features for the prediction. So these are the corresponding algorithm, and we could represent this through, and here we may notice this is a hormonal conceptive years. This played an important role for cancer prediction. So the importance of each of the features of the predicting cervical cancer with a random forest. The most important feature was hormonal conceptive year for here. Permuting hormonal conceptive year resulted in increasing one AOC by a factor of 6.13, which is shown from here. So this is actually loss 1 by. So permutation features importance. It's a nice interpretation. And feature importance is the increase in model error when the features information is destroyed. Feature importance provides highly compressed global insights into the model's behavior. A positive aspects of using the error ratio instead of the error difference is the feature importance measurement. The comparable across different problems, and the importance measure automatically takes into account all interaction with other features. So the another point, permutation features important does not require to retain the model. You could just feed the corresponding features to the black box model, and you will get the corresponding output, and from the output you could decide that one. Disadvantage: you need to access the true outcome. The permutation features importance depends on sampling the features, and which adds randomness to the measurement. Obviously, you could understand. When the permutation is repeated, the results might vary greatly. If features are correlated, the permutation features importance can be biased by unrealistic data sets. So another is global surrogate model. We have discussed these things at the beginning. A global surrogate model is an interpretable model that is trained to approximate the prediction of the black box model. So we have an entirely black box model where we do not know what is there. So we can draw conclusion about the black box model by interpreting the surrogate model, means solving the machine learning interpretability by using other machine learning models which are already known as interpretable model like a decision tree and etc. We want to approximate our black box function f as closely as possible to the surrogate model prediction function g under the constant, and that g is interpretable. For a function g, any interpretable model can be used like linear model or decision. So here selected dataset X. This can be the same dataset what was used for training the black box model, or a new dataset from the same distribution. This is important. You could utilize the same training set, or you could use the different dataset. You could even select a subset of the data, or a grid of points depending on your application. For a selected dataset X, get the prediction of the black box model. So you are not changing any value of the parameters. Let's suppose this is a neural network. You are not changing any values. You are just fitting the corresponding features, and you are getting the corresponding output, the predicted class. Now, using those particular predicted class, that is the test, the output class, and this one. So this is different from actual training level. Because training data set is, if you are considering the training set is fixed. But the output class, this output class is now the predicted class instead of the target class. And now this predicted class will be used for training another interpretable model that is like a decision tree, and it makes a prediction. And if that model predicts properly, perfectly, then you could say this is your interpretable model against the corresponding black box model. So you could say measure how well the surrogate model replicates the prediction of the black box model into the surrogate model. So these are the some you can say random forest things, and here the corresponding decision tree output. So random forest, you know, it is a combination of multiple decision tree. It would be decided, but whenever you are using a single decision tree, then you could easily describe them. For example, for these particular cases where sexual transmitted disease less than 0 years and hormonal contraceptive years less than is equal to 9, then healthy chance is high, whereas cancer chance is very low. Now hormonal contraceptive years greater than 9, now cancer chances become, healthy chance become low. And now this way, if sexual transmitted disease greater than 0 years, then because the cancer chances become more, healthy chances is not too good. So time randomness of a surrogate tree that approximate the prediction of a random forest trained on the cervical cancer data set. The counts in the nodes show the frequency of the black box model classification in the models. Now, global surrogate model, advanced surrogate model method is flexible, but the approach is very intuitive and straightforward. With the R-squared measure, you can easily measure how good our surrogate models are in approximating the black box prediction. Disadvantage, you have to be aware that you draw conclusion about the model and not about the data, since the surrogate model never sees the real outcome. And even it is not clear what is the best cutoff for R-squared. Is in order to be confident the surrogate model is close enough to the black box model. It could happen that the interpretive model is very close for one subset of the data set, but widely divergent for the another data set. So interpretive model you choose as surrogate comes with all its advantages and disadvantages. So any question till now? We are now start a model agnostic methods for our lookup. Any question? Is there any question here?
No, sir.
Okay, now we could start model agnostic methods for the local. So here individual conditional expectations plots display one line per instance that shows how the instance's prediction changes when a feature changes. So here we could say PDP partial dependency plot is the average of the lines of an IC plot. So, but a PDP was for the global, but here for single prediction we could utilize. But for each instance, the curve FC is plotted against XSI while XI remain fixed. But it is hard to tell sometimes. The IC curves differ between individuals because they start at the different prediction. So for this, actually centered IC plots are preferred. If cap centered, if I minus 1 is the corresponding vector, appropriate number of dimension, usually 1 or 2, and XA, XI, this is the center point. So you will get this kind of curve from there. IC plot cervical cancer probability by age. This is for the with respect to age. And here PBS, here every line is considered for each samples. So how many samples are there, that number of lines will be considered. For some women with the predicted cancer, probability above 0.4, prediction does not much at higher age. Now this is a centered plot, IC plot for predicted cancer probability by age, and lines are fixed to 0 Here it is a fixed to 0 and age is here 14. So the predictions or the most women remain unchanged until the age of 45. Where prediction probability 45, then it is the probability is increasing. So advantages, conditional expectation curves are even more intuitive to understand than partial dependency plot. IC curves can uncover heterogeneous relationship. Disadvantages, IC curves can only display one features meaningfully because two features would require drawing of several overlaying surface and you would not see anything in the plot. So you could understand from there, this is for only one features and what will happen if you have multiple features. If the features of interest is correlated with other features, then some points in the lines might be invalid data points. According to the joint feature distribution, if many IC curves are drawn, the plots can become overcrowded and you will not see anything. And that's why IC plot might not be easy to see. Now, the most important or most popular rather, local interpretable model agnostic explanation, that is LIME. LIME is used heavily in the domain of interpretable machine learning. So LIME actually is a local interpretable model agnostic explanation. Here, local surrogate models are interpretable models that are used to explain individual prediction of black box machine learning models. Surrogate models are trained to approximate the prediction of the underlying black box model instead of training a global surrogate model. LIME focuses on training local surrogate model. Local surrogate means here you have to provide a single prediction, single samples, and their prediction value will be considered for explanation. LIME test, what happens, give you a variation of data into the machine learning model, a new data set, and how it would be generate a new data set will be discussed later. So this is mainly from the paper Why Should I Trust You? Explaining the predictions of any classifier of 2016. Now, what do you mean by the trust? Trusting a prediction whether a user trusts sufficiently to take some action based on it. Trusting a model whether a user trusts a model to behave in a reasonable way if deployed. So, for example, here, so this is model data prediction flu, sneeze, weight, headache, no fatigue. External line, sneeze, headache, no fatigue. They will human makes the decisions. So, textual and visual effects to provide the qualitative underlying of the relationship between the instances component and the model prediction. And algorithm on atheism, the first cases is about some atheism, but second cases it is a posting host and etc. They are used, but the prediction become correct at both the cases. But explanation are different. Why do we need trust and integrity? Sometimes model can go wrong in a way that obvious to human. Data leakage, patient ID being correlated with the target class. Dataset shift, training data is different than the test data. And exploiting feature, user may favor recommender system that do not exploit or clickbaits. So these are text-to interpretable, local fidelity, at least locally faithful, model agnostic, the ability to explain any model, global perspective, ability to explain the model, not just a single prediction. LIME as interpretable framework. This is the corresponding formula. This is let's suppose this is the epsilon. This as ix is the corresponding instance and a measure of unfaithfulness. This is loss function. This is will be our minimum. So interpretable model to be explained, and this is the corresponding local model, and this is the corresponding complex model. And how many samples we will consider, this is the proximity of the measure to the defined local. So this is model is like let's suppose here. Let's suppose we are considering a single samples here. Now here we are making a decision this line, and then we could make some approximately there is some other data samples here, different data samples, and we'll try to predict them using this classifier, because this could be easily identified by decision tree, and now you could use this complex model, that is the F, and this is you could say this is the main model, that is the F, and this is the corresponding G, and you could use all the samples using F and G, and then you could make the decision here. So F, G, and X proximity measure to the defined locality, and there is a complexity measure, how much complex the model will be. Decision will be from there, and text binary vector indicating presence or absence of word, image binary vector indicating presence of absence or contiguous patch or similar patches, original representation, interpretability representation, this would be like there. So X dash sampling local area Z dash, and inverse representation Z is an obtained level. So here one using this local representation, you could be using the J, and here sample around X dash by drawing non-zero element X dash uniformly at random. This is very important, as we discussed, and the number of draw is also uniformly sample. Z dash basically has a fraction of non-zero elements of X dash. Samples are weighted by X. So line procedure: select your instance of interest for which you want to have an explanation of its black box prediction. Perturb your dataset and get the black box predictions for these new points. Weight and new samples according to their proximity to the instance of the interest. Train a weighted interpretable model on the dataset with the variations. Explain the prediction by interpreting the local model, and you could notice from there. So, and sparse linear. So classifier if the number of samples instance X and its interpretable version X dash, similarity kernel pi X, and length of the explanation K. So we'll get this one Z, and sometimes if you have a number of features are less, so sparse, so features are high compared to the number of samples. On that case, you could use K lassos to select K number of features using the lasso method as described earlier. So some results of the line, you may notice this is a explain acoustic, explain labrador. So we do not have too much time. We could not discuss these things, but for image data, actually you could select a particular section image, and you could classify them. You could then off them. You could select other section. You could off on. In this way, you could get the proper one and identify the corresponding weight of the features, or here for the image super pixel, because single pixel could not determine anything. So advantage of line, even if you replace the underlying machine learning model, you can still use the same local interpretable model for explanation. Using lasso short trees, resulting explanation are short, selective, and possible contrastive. Lime is one of the few methods that works for tabular data, text, and images. The explanation created with local surrogates models can use other interpretable features than the original model was trained on. Disadvantage: the correct definition of the neighbor is very big unsolved problem. When using line with tabular data, data points are sampled from a Gaussian distribution, ignoring the correlation between the features. This is important point we are missing during the calculation of the line. Complexity of the explanation model has to be defined in advance, and line explanation can be manipulated by data scientists to hide the bias. Another is Shapley value. We do not have too much time. Just the concept is like that. In a game theory, if you have a multiple in a team, let's suppose there is 4 players, they win a particular gamble, then or a particular competition, then how the share prizes will be distributed among them. So in general way, you could divide them equally, but it might not be the case, because those who are expert are there, they could say that I have contributed more, I need some more value. Oh, okay. So on that case, how it would be determined? So on that case, it would be determined by using the effects of everyone in that particular process. So it would be considered that against everyone. Let's suppose one person is compared with others, just person, then other person, the person with other person, differently it will compare. And let's suppose here one person is compared with one person is compared with all three, one person is compared, this is overall, this is one person, only one, and this is this another person, this is another person. So this is another one. So in this way it will consider all kind of combination, averaging the, and it will calculate the corresponding effects of that particular features. So this would be calculated. There is a value. So supply value is defined by value function val of a player in S. S is a subset of the feature used in the model. X is the vector of the feature values of the instance to be explained, and P is the number of features. Val Xs is the prediction for the feature value in the set S, and the are marginalized over features that are not included in the set. So value is S, and all kind of combination consider, and you will get some. There is no time. So there are some particular algorithm. It is purely the particular algorithm is available in the internet. So in this way, and Shapley explanation is this is Shapley value. We could get some kind of weight about the corresponding features, and Shapley adaptive explanation method explain the individual prediction is based on the game theoretical here. We use the phi 0 and this phi j. So here G is the explanation model, JJ is the coalition vectors, and M is the maximum coalition size, and phi j is the feature attributes or Shapley value of the features. So this way we could get the Shapley value from there, and we could, and that these are some explanation for the prediction 0.06. These are the things. So now we could explain. Okay, so these particular slides are mainly made from the books Interpretable Machine Learning by Christopher Moore, and there is a particular course Explainable AI from simple predictor to complex generative model, Harvard University. And practical application, we have utilized a very simple concept, that is how to define a particular cytology images. So if you notice, there is a base cytology, some benign samples. So in benign samples, the particular cell size are more or less uniform, but there are staining, different types of stainings are there. Path staining, middle staining, middle and right MGG stainings are there. So these are some malignant samples. If you notice here, in malignant samples, the size varies. Here size, this is a varies. This size varies. This is a bigger, small. Variations are very high, right? So now, if you in general, if you fit any deep learning model, your model will recognize them properly. Then how could it would be defined? So for these cases, normally GATCAM clusters, these are the popularly utilized, and this is for a cervical cytology images. So cervical cytology images. Here different types of cells are there. This is department database. It is not the standard one, but there are different types of cells you could notice. Then how the machine will understand these cells. So if you want to recognize the cytology domain, there are lots of challenges, especially some overlapping regions, huge color variation, accurate prediction. So all this could be identified from the heat maps, and these heat maps could be calculated after getting the prediction using the GATCAM. So we do not have time, so we could stop here. These are some results, and these are from the papers. Here, if you notice, these regions are highlighted during the classification. Okay, so that's all for the today. Is there any question?
Thank you, sir, for the presentation. Sir, kindly share this presentation with us.
Hello? Is there any question? So I would like to thank my three scholars who helped me to develop these slides. Thank you for your patience. Any question?
Thank you, sir, for your much insightful and thoughtful session. Your expertise and perceptions on the importance of transparency and trust in AI models have been enlightening. Now, I would like to invite Sumanto Chatterjee, sir, Assistant Professor of the Computer Science and Engineering Department at JS College of Engineering, to deliver the vote of thanks. He is a distinguished faculty member, having published two books and authored many papers internationally. Sir, we are honored to have you here. Sir, over to you.
Thank you, Chirag. Am I audible? Hello.
Yes, Sumanta, you are audible.
Yeah. So thank you, sir. Thank you for your informative session. I would like to extend my heartfelt thanks for your enlightening presentation during the webinar. Your expertise and the insights were truly invaluable, and I found the session both informative and inspiring. So once again, thank you, sir, for your sharing your expertise with us. I would like to thanks all the participants, those who have already joined in this session. Okay, so I think that you have already got the that much information regarding this field. And please convey my thanks to the entire team involved to putting together in this event. It's clear that a lot of effort and the dedications went into making it a success. Thank you once again, sir, and thank you all the participants. Thank you all the organizers for to make this event successful. Thank you all.
Thank you.